Recording started.
Okay, good evening everybody, and welcome to another session of organic chemistry. Before we start, a couple of announcements. Tomorrow we are going to have the review session tomorrow instead of Monday, because I want to give you guys a chance to view the webcast over the weekend, so that you get a chance to use the webcast to study. So we have the review session tomorrow at 8 p.m. Those of you, if you cannot join us, I will post the webcast in Blackboard before I leave tomorrow. So that gives you the whole weekend to get a chance to look at it. Okay? So that is tomorrow, Friday, January 27th at 8 p.m. And I will send you a reminder. The link that we are going to use will be the same link that we use this Wednesday. Indeed, that is the link we are going to use for the rest of the semester. Okay. Of course, you know the first exam is scheduled for Tuesday next week. Okay. So now let's see what we can do with the quiz that you have just taken. So we are going to go over the quiz before we finish up on chapter 16. Okay, the problem in number 1, I know many of you will find it difficult to read, but I do know that Jessica has very good eyes. Jessica, go ahead and read that question for us. Okay, very good. From the reaction sequence, the expected product will be, okay, what is the reaction they've given us? We have this here. They start with toluene, this molecule here, and then they perform what kind of reaction did they perform? Bromination, okay. So with iron 3, some iron 3 salt. And so what will be the product? What do you expect the product to be? Auto and para product. Very good. So we expect to get, because the methyl group is an auto para director, so we expect to get 2 products. So we have the auto product and the para product. Okay, now they take this product. They take that product. In the next step, they now react with potassium permanganate. Okay. So we have Potassium permanganate, in this case in sodium hydroxide. Sometimes it is used in the presence of acid. Okay, so what do you expect as the product? Carboxylic acid, okay? So the methyl group will be oxidized to carboxyl group, right? Okay, so we have two products. So this is nothing but a case of memorization, right? You just have to know this. Carboxyl group, bromine here, and the second product, and bromine in the para position. Okay, now after that, what did they do? They now take this product here, they perform another reaction. And what type of reaction are they performing here? Nitration. Okay. Okay, so what kind of product do you expect? What kind of product do you expect here? Okay, let's start with this one here. What kind of product? Which substituent would direct the incoming group? Bromine, okay. And bromine is an auto-para director. So we have bromine here, and therefore we expect the nitro group where? Right here. Okay, and then if you look at this one here, we have the carboxyl group here, the bromine here, and the possibility that we could get what? Get something here, right? Okay. Okay, so what series of products, what are the choices we have here to see which one will work? Which are the choices? Which is the correct answer here? Which one? 4. 4. This is the answer they've given us. And do we have it here? Do we have 4? Yeah. And that is this one here. So this question is not as innocent as it looks. You have to go through a bunch of reactions to actually get to the solution. Yes, that's Jasmine? Okay. Say that again, loud. Oh, okay. Is for this step? For this one here, okay. The question Jasmine is asking, how do we know that the bromine will be the director? Because we know that we have a carboxyl group. The carboxyl group is a metal director, and the bromine is an auto-para director, and bromine is a moderate deactivator. On the other hand, the carboxyl group is a strong deactivator. So the bromine will be the director here. Okay? Okay, so that is the answer to that. So the key to this is you must know those reagents and what they do. I know some of you who were in my class last semester, You got tired of me saying that. But that is the truth. You have to know what those reagents do. Make up a table of reagents and say, what does this reagent do? Okay? Once you do that, most of your problem will be solved. Okay. Okay, but number 2, Dylan, go ahead and read number 2 for us.
A phenol is...
Yeah, a couple of them.
An OH group attached to a benzene ring, 2 benzene rings joined by an oxygen atom, an OH group attached to a double bond of an alkene, or an OH group attached to an sp3 hybridized carbon atom. Okay,
very good. So what is the answer? Everybody agrees? The OH group attached to a benzene ring, correct? Okay, so that is a phenol. So 1 is the correct answer. A phenol is a molecule in which the hydroxy group is attached to a benzene ring. Okay, very simple. Okay, how about this here? Shine, can you read this for us? You can. Okay, let's see. Who has some good eyes? Who has some good eyes here? Okay, okay. Karis, go ahead.
With a mixture of concentrated nitric and sulfuric acid below 50 degrees Celsius with humidity.
Okay. So here the reaction of toluene with a mixture of concentrated nitric acid and sulfuric acid below 90 degrees gives mainly. Okay, so what do they have there? They are telling us that you are, once again, we are starting with toluene. And they say that they start with toluene and then they want to do nitration. So you start with nitric acid in the presence of sulfuric acid. You don't really need to know the condition in terms of 90 degree and whatever. Okay, the question now is, what will be the product? What will be the product? What is the product? Huh? Also para-director nitro toluene, right? Okay, good. So this should be a very simple one. Everybody should be able to get this right. So you have the para product here, and then you have the auto product here. Okay, do we have that here? Where's the answer here? 5? Okay. Okay, very good. Okay, so 5 is the answer. Okay, Simone, go ahead and read this for us. Okay. Draw structures corresponding to the following names, right? Very good. Okay, this is not 20 points for this quiz. The quiz is only worth 10 points, so. Okay, so what is the answer to this? Okay, we have p-chloroaniline. P-chloroaniline. What is the first thing you need to know? What is the base name? Aniline. Okay, so you need to know the structure of aniline, right? Do we know aniline? What is aniline? Benzene with an amino group. Very good. So you know that. That's aniline. Then they say P In other words, this will be in the parallel position. 3-chlorobutyl. Okay, so you have a complex substituent. So it is a butyl group. So 4 carbon. That's a butyl group, right? Now there's a 3-chloro. Okay, since this is a substituent, this is carbon number 1 for that substituent. Okay, let me number that. This is carbon number 1 for the substituent, carbon number 2, carbon number 3, carbon number 4. So what that is telling us, the chlorine is attached to carbon number 3 of the substituent. Okay, so what we need to do, remove an hydrogen here, 3, and then place a chlorine atom there. Is that right? Okay, if that is correct, give me a happy face. Okay, I see the happy faces now. Frowning faces. I see a couple of frowning faces. I will actually see live frowning faces and happy faces. Okay, very good. Okay, so that is the answer to that. Okay. Okay, let's do B. This here. 3-bromo 2-methyl benzoic acid. Everybody should get that right. This is benzoic acid, which is the base name. There is a 3-bromo. That means bromine is here. And 2-methyl. That means methyl is here. This is the carbon number 1, 2, and 3. Okay, is that correct? Okay, happy faces again, right? Okay. Now let's do this one here. C. 4-isopropyl 3-nitrobenzaldehyde. What is the base name? Benzaldehyde. Okay, very good. That's benzaldehyde. And then we have 4-isopropyl. So we have the isopropyl in the 4th position. Okay, then we have 3-nitro. So all of these should be fairly simple to each one of you. Right? Okay. Okay, now let's do the last one here. D. Let's do D. 4-chloro-2-propobenzene sulfonic acid. Okay, what is the base name? Benzene sulfonic acid. Okay, very good. That's benzene sulfonic acid. We have 4-chloro, 2-propyl, okay? And so I think all of you should find nomenclature fairly easy to do. Yes. Do one. Okay, 3. Oh. Thank you. Yeah. Okay. Now, this is the question of the day. This is the quiz right here. The rest of them were just they were just warm up, right? Okay. Let me see. Emma, go ahead. Oh, you are going to ask me a question? Huh? Yeah, go ahead, go ahead. No, read the question first.
Provide a synthetic scheme for the following transformation to name the process.
Okay, now go ahead.
Okay, so I first did Friedel-Crafts acylation.
Okay, Friedel-Crafts acylation. Why did you do that?
Because I wanted to put a ketone there so I could then the chlorine to be netted to it, so I did chlorination next.
Okay, very good. So you say that
Well, I did so it'll go down to C, down to CH2, down to CH3.
oh, CH, okay, right. Okay.
And I did chlorine.
So you get the product from Friedel-Crafts acylation, okay? And the reason why you do that is because that is a metal director, okay? Okay, folks, let us go through that again. Emma started with Friedel-Crafts acylation because he is looking at the relationship between this group and the chlorine, right? It's a metal relationship to each other. The only way you're going to be able to do that is to have something metal director here, right? Okay, very good. So that is why you did the acylation first. Okay, then you follow that with
chlorination.
Chlorination.
CO2 and CO3.
Chlorination with some iron 3 salt, okay? And then you get the metal relationship established, okay?
Then I did
now the chlorine goes to the metal position, okay?
Then I did reduction of the ketone.
Okay. Now you did catalytic hydrogenation of the ketone. And that gives you the propyl group here.
And then I did
So here the carbonic gets reduced to a CH2, okay?
then I did sulfonation.
Okay, then you do sulfonation. And for that you use,
SO3.
okay, sulfur trioxide in the presence of sulfuric acid. Okay, excellent. Very good. Do you all agree with this? Okay, the only way you can do this is when you know those individual reactions. If you don't know the individual reactions, there is no way you can do this. Okay, yes.
Does hydrogenation reduce the sulfonic acid phase?
No.
So I really could have done that last.
Yes, you could have done that last, yes. But from my experience, you know, working in the lab, you probably did the best thing to do it first. Okay. 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 We don't need to do this. I think everybody should be able to do this. Go ahead. Okay. You don't want me to cover the rest of the... You need to do this one here. Okay. Okay, Ambria, go ahead and read it.
I was saying you didn't name it. You tried to name it at first.
To name the product. Okay. Well, I figure you guys know the names already. Okay, so what is the name? Ambria wants us to name this. Ambria, go ahead and give us the name. Okay. Give us the name. What's the base name?
4-chloro.
Okay.
2-propyl.
Okay.
Benzene sulfonic
4-chloro. 2-propyl. Benzene sulfonic acid. So you know the name. She just wants me to do some work, that's all. Okay, she's trying to slow me down. I know what that is. Okay, very good, very good. Okay, Ambria, go ahead and read this.
Mr. Resonance structures show why methoxyl group is an ortho or para director and not a meta director in electrophilic aromatic coordination of methoxybenzene. Assume that the electrophile.
Okay, very good. Okay, does anybody know how to go about doing this?
You have to show that, you show all the resonance structures and show how one of the resonance structures is impossible.
Exactly, exactly. So in other words, we need to draw the reaction mechanism. Okay, the first thing we need to know is to know the structure of anisole, which is methoxybenzene. Okay, what kind of director is methoxy group? Also para director. Okay, so what they want us to show here, why is it an auto para director? So let us choose the para position just for, because the last time we did this, we used the auto position. So let us say the chlorine is here, it's coming. Chlorine is your electrophile. Okay, we want to use the chlorine to go in the para position. We take the pi electron, attack the electrophile. Keep in mind that electrophile could be anything. Any species that is positively charged could be an electrophile. Okay? So what do we have? We have, well, you know that you are going to get this type of problem in your exam. There's no way around it. So you have the methoxy group. Now we have the double bond here. Another double bond here. And since the chlorine is coming to the para position, it's here. And of course we know that the hydrogen was here. So just for the sake of bookkeeping, let's put the hydrogen here. And so that hydrogen is still here. And we also know this hydrogen is still here. And what happens to this carbon? It becomes a carbocation, positively charged. Okay, very good. Okay, so now we obtain that. Now we need to draw resonance structures to show why the methoxy group will stabilize the resonance. Okay, so we now draw a resonance structure. Move this electron to here. Okay. By the way, we know we have non-bonded electron on oxygen, so we might as well go ahead and do that here. Okay, so what happens here? We have the double bond is moved to here. The positive charge is here. This double bond is still here. hydrogen here, chlorine here, and this hydrogen is still here. Just for bookkeeping, let's keep everything in place. Now, at this point, we want to draw another resonance structure. Okay, we could draw two resonance structures at this point, but let us do the one that involving the oxygen. The point we want to make here is oxygen is involved in the resonance stabilization of the carbocation. Okay, so we are going to move this to here, this non-bonded electron to here, so it now form, and we will transfer the positive charge to oxygen. Okay, so that is another resonance structure. So as long as we could, whenever you do this, if you can show that your resonance structure involves stabilization due to the atom that is attached to that carbon, then you could justify why it is an auto or para-director. In this case, why it is a para-director. Of course, we know there's another possible resonance structure here. If we do this, move this to here. This goes here. Okay, and then the positive charge is here. Chlorine is here. Hydrogen here. And this hydrogen is still here. Now, at the end of this process, of course, we know that what is going to happen. Keep in mind that when you form the electrophile, there is a base that goes with it. For example, how do we form the electrophile? In this case, we have chlorine in the presence of ion 3. This ion is the ion 3 chloride is a Lewis acid. So what does it do? To attract this electron to itself, and so okay, so as you know, we have finished chapter 16. All I want to do is just do a little bit of summation on this the rest of the chapter. As you can see here, this is the generic mechanism for electrophilic aromatic substitution reaction. Okay, we've done this several times already. You see the electrophile is attacked by the pi electron on benzene. You form your intermediate carbocation. And then, of course, you could draw resonance showing the different resonance structure for the intermediate carbocation. And then finally, you have a base. We pull off right here. The base will pull off this hydrogen, thereby releasing the two electrons to regenerate the aromatic ring system. And that is your classic aromatic electrophilic aromatic substitution reaction. Now, by now you know that we have been able to make all of these classes of compounds. Okay. So far we've shown you how to make the nitro group and nitrobenzene through nitration. Halogenation, we show you how to do those. Sulfonation, you know all of the reagents to do this. Fiddle-crab acylation, Fiddle-crab alkylation, And now in each one of these cases here, the electrophile is positively charged. As you can see, the bromonium ion, chloronium ion, iodonium ion, carbocation. We call this the ethylene ion. This is this one here. Okay, that's when you pull up the chlorine. Of course, this is the nitro, and this is the sulfonic acid ion. Okay. Now, how do you form all of those ions, electrophiles, rather? These are the various ways in which you form them. In the case of bromine, you use ion 3 bromide. That pulls the bromine away from the bromine-bromine bond to form the bromonium ion. The same in the case of iodine with the copper 2 ion. What happens here, the iodine will transfer 2 electrons to the copper ion, reducing the copper 2 to copper 1, and in so doing you form the electrophile. Yes?
The copper 1 acts as a base, so you're not supposed to.
Okay, do not forget there is a counter ion here. This one is generally, this copper will be copper Cl2. It's in solution. So here you have the chloride will be in solution. And that chloride will act as a base. Okay. The question that Emma is asking is, what acts as a base in this particular instance? Okay, I just told him that in this particular instance here, the complete compound that is used will be copper 2 chloride, and of course the chloride ion will be in solution, and the chloride ion therefore will act as a base. Okay, here for the nitration, you have nitric acid. This is the structure of nitric acid. Okay, the reason why you need sulfuric acid here, sulfuric acid will protonate the oxygen of this hydroxy group. Okay, and once you do that, it loses water very readily to form the nitronium ion. And the nitronium ion now reacts as the electrophile. Okay, and in this case, the water now acts as a base to pull off the proton from the intermediate carbocation. In the case of sulfonation, this is the structure of sulfur trioxide. Okay, the sulfuric acid simply protonates this oxygen here, and there you have the sulfur is positively charged, and that acts as an electrophile, and that continues the process. Keep in mind that once the electrophile is formed, the mechanism is the same for each one of them. In the case of the Friedel-Crafts alkylation, okay, here you generate also the carbocation by pulling the chlorine, the bond between the chlorine and the carbon, pulling that away from carbon to form this complex here, and in so doing you form a carbocation. Okay. Now in the case of Friedel-Crafts acylation, if you have this, and you have aluminum chloride. Okay, what happens here? This is a Lewis acid, draws this electron to itself, and in so doing, and will thereby weaken this bond. And so you end up with this here. And this is what you call your ethylene. Ion. And the ethylene ion then goes on to act as an electrophile. Okay? Okay, you don't need to worry about all of this. This is just some experimental data. Same here. Okay, the last, well, 2 more reactions will give you this and 1 more reaction, and that will be the end of chapter 16. We also have nucleophilic aromatic substitution reaction. This is not a reaction that occurs readily. Anytime you have a benzene molecule in which you have an halogen attached to it, and you also have electron withdrawing group also to the halogen, or it could be chlorine, bromine. Anytime you have an electron withdrawing group, like in this case you have a nitro group, you could get what we call nucleophilic aromatic substitution. Why do we call this nucleophilic? Why nucleophilic instead of electrophilic? Because the species that is attacking contains electron, has electron. It's a nucleophile. In other words, it is rich in electron. Okay, in this case we could use hydroxide. Okay, any species that is rich in electron could do this. Essentially, will attack this carbon here. What is the mechanism for this? The next process is we are going to substitute the halogen for the nucleophile that is going to attack. Okay. And the example of this is what happens here if you want to look at the mechanism for this. If you have this case, say you have chlorine here, and you have electron withdrawing group here, what happens is that because of the electron withdrawing nature of this group, it draws this electron to this carbon, and in so doing, the negative charge is on this carbon here, and thereby you have a positive charge on this carbon. And so at this point the nucleophile will come in. Let's represent the nucleophile as Nu. It could be any species that is negatively charged. The nucleophile comes in, attack this carbocation that is formed, and of course you form this. The nucleophile is here. Keep in mind, this is the negatively charged. So now that negatively charged carbon now wants to regenerate the benzene, the aromatic ring system. To regenerate the double bonds, so does this. And when it does that, one of these has got to go. You see that the nucleophile will leave or the chlorine will leave. In this case, the halogen will leave. And that is how this reaction happens. So the net process is substitution reaction in which you are using a nucleophile. But this reaction only occurs whenever you have a leaving group attached to benzene ring and an electron withdrawing group is auto to that leaving group. That is the only time this reaction occurs. Okay? And finally, before we finish this,
It only occurs in a leaving group is attached to a benzene ring and what else?
okay, this reaction only occurs when you have a leaving group, in this case the chlorine, okay, that is, the leaving group is on benzene, and also to that leaving group must be an electron withdrawing group, like a nitro group, for example. Okay? Yes. Oh, yeah, that's good. And yes. Should be NU. Okay, that's Jessica just told her that should be NU, right? Okay, thank you. Okay, so now that is nucleophilic aromatic substitution reaction. Okay, you've seen this before, the side chain reaction. You've actually seen this before, the reaction in which if you have remember last semester we did this, if you have a benzylic hydrogen, this is benzylic carbon, and any hydrogen attached to the benzylic carbon is called a benzylic hydrogen. So anytime you have a benzylic hydrogen, you could use what we call MBS, which is N-bromosuccinimide, in the presence of a peroxide. A peroxide is any species in which you have two oxygen atoms attached to each other, and each one of them is attached to a carbon atom. That is a peroxide. Or sometimes it could, instead of the oxygen being attached to a carbon atom, it could be attached to hydrogen. For example, hydrogen peroxide. I'm sure you guys used hydrogen peroxide before, right? Okay, you could use hydrogen peroxide or any other peroxide. So the point here, you take MBS in the presence of a peroxide. What does that do? It replaces a benzylic That benzylic hydrogen must be, of course, attached to an sp3 carbon. So you end up with this here, with bromine. Okay? So supposing we have this, okay, that benzylic hydrogen must be attached to an sp3 carbon. Supposing we have this, and I give you MBS in the presence of a peroxide, what will be the product? What will be the product? What is it? Yeah, there is. Okay, very good, excellent. Okay, so David has given us the answer here. This here. And now, based on what we did last semester, we could now take this and convert this to an alkene. Remember? We could do dehydrohalogenation, convert this to an alkene. So that is an excellent route. That's a good route to okay. Right? And of course, based on what we did last semester also, Supposing we add borane followed by what? Hydrogen peroxide. What do you expect to get? Hydration, exactly. So this is a way to get us to, from benzene, all the way from benzene, we could make this molecule, right? So you begin to see some of the things that we could do with this. Anyway, that is the end of chapter 16, unless you guys have any questions. So I will see you tomorrow. You do owe me. I'm giving you back here 5 minutes. So you owe me 5 minutes. You owe me 5 minutes. So I will see you guys at 8 o'clock tomorrow. For those of you who want to join us, and I will post the material in Blackboard so that you have a chance to review the material for the exam over the weekend. So enjoy the rest of your day.